All right, so today we're going to pull back the curtain and see what it really takes to build a modern industrial engineer. We're going to deconstruct their entire education piece by piece to understand how they learn to see the world in such a unique and powerful way. I mean, really think about that for a second. You've got this one little piece of metal, but before it gets anywhere, it has to be designed, the raw materials have to be sourced, it's got to be forged, machined, tested, packed up, shipped, stored, all to arrive at a factory at the exact right moment. How does that incredibly complex dance happen flawlessly millions of times a day? Well, that's where the industrial engineer comes in. They're the ones who are actually designing, managing, and constantly improving these massive interconnected systems. You can think of them as the architects of efficiency, the people who turn potential chaos into a beautifully tuned global machine. So how do you even begin to build a mind that can do all that? Well, we're going to follow the roadmap of their curriculum, layer by layer. We'll start with the absolute fundamentals of physics, then get into the tools they use, the strategies they deploy, and finally, the real-world context that ties it all together.
Okay, first things first, the foundation. Look, you can't optimize a system if you don't fundamentally understand the rules it plays by. For an industrial engineer, that means you have to start with a deep, mathematical mastery of physics, the core principles that govern energy, motion, and matter itself.
So let's take something like the Fourier transform, which comes straight out of their advanced math courses. Now, this might look like just a bunch of abstract theory, but it's an incredibly powerful tool. It lets an engineer break down really complex signals, like the vibrations in a machine, into simple, easy-to-understand parts. This is literally the bedrock of modern diagnostics and control systems.
And this is where it all clicks, right? This is how you bridge that gap from pure theory to hard reality. Thermodynamics isn't just a formula on a blackboard. It's the reason an engine generates power. Fluid mechanics isn't just about flow rates. It's how you design a pump that can move thousands of gallons of water with maximum efficiency. This knowledge isn't just academic. It's the language they need to understand every single machine they'll ever work with. So, once you've mastered the laws of physics, the next layer is the toolkit. We're talking about the actual machines and automated systems used to shape and control the physical world. This is where theory gets its hands dirty. What's cool is that the curriculum covers this whole evolution of manufacturing. You learn the fundamentals on conventional tools like lathes, where you're feeling the metal and it's a real hands-on craft. But then you master digital manufacturing with CNC machines and PLCs, programmable logic controllers, which are the brains that automate entire assembly lines, where absolute precision and repeatability are everything. So how do you actually talk to one of these multi-million-dollar machines? Well, you have to learn its language. This is a breakdown of NC part programming. You use specific commands like G codes for the geometry and M codes for machine functions to write a literal script that tells a block of aluminum exactly how to become a precision engine part. And this is where the scale just becomes mind-boggling. An IE's toolkit isn't just one machine. It's about orchestrating an entire symphony of automation. We're talking fleets of automated guided vehicles gliding silently through a warehouse, robotic arms assembling products with superhuman speed, and massive retrieval systems that can find one tiny item out of thousands in a matter of seconds.
Okay, now we get to the absolute core of it all, the strategy. I mean, having the best machines in the world is totally useless if they aren't working together efficiently. This is the world of operations management, and it's where the IE's focus shifts from managing one machine to orchestrating the entire system. I love this quote because it's pulled right from the course objectives. It gets to the heart of it. The goal isn't just to make things run. It's to create strategic thinkers who can look at a whole system, find the one tiny bottleneck that's holding everything up, and make a smart, data-driven decision to fix it. And a huge part of that strategy comes down to a fundamental choice. How do you manage the flow of work? This table shows two different philosophies. The old-school push system is where you make stuff based on a forecast, which, often leads to warehouses full of stuff nobody's buying. The pull system, which is key to lean and just-in-time, means you only make something when a real customer actually orders it. IEs have to know exactly which system to use and when. And their strategic toolbox is just packed with these powerful methodologies. You hear buzzwords like lean, kaizen, and just-in-time all the time. But for an industrial engineer, these aren't just buzzwords. They're concrete, structured systems. Each one's a different lens for looking at an operation, a tool for systematically finding and destroying every single ounce of waste, whether that's wasted time, materials, or even motion. But here's the thing. Pure, raw efficiency isn't enough anymore. The modern industrial engineer has to work in the context of the real world. Their decisions have huge impacts on people, on the planet, and on the bottom line, and their education has to prepare them for that responsibility.
This is what's known as the triple bottom line, and it's baked right into their training. Through economics courses, they learn cost-benefit analysis. Through ethics courses, they study the social impacts of their work. And through sustainability courses, they learn how to analyze the entire environmental life cycle of a product, from cradle to grave. One of the most important concepts shaping the future right now is the circular economy. This idea completely flips the old take, make, waste model right on its head. Instead of a one-way street to the landfill, an IE trained in this philosophy is constantly asking, how can we design this product so it's easy to take apart and reuse? Or how can we create a supply chain that brings materials back? It's a total paradigm shift. And this, of course, creates a massive challenge, but also a huge opportunity. How do you design a smartphone that can be 100% recycled? Or a global food supply chain that creates zero landfill waste? These are the giant, complex questions that modern IEs are being trained to solve. So, after you've gone through all these layers of training, the physics, the tools, the strategy, the real-world context, what do you end up with? You get something truly special. You get the complete system thinker. And this, right here, is the whole point. An industrial engineer is trained to constantly zoom out. They see the gear, but they also see the machine it's inside of. They see the machine, but also the factory it's running in. They see the factory, but also the global supply chain it depends on, and ultimately its total impact on the world. It's that unique ability to move between every single level of a system that makes them so valuable. Which really leaves us with one final big question. As our world just keeps getting more complex, more interconnected, from logistics to data networks to resource management, what's it going to be? What will be the next great efficiency challenge that demands the unique vision of an industrial engineer to solve?